Before attempting to understand Faraday's law of electromagnetic induction, we should recapitulate the terms used in electromagnetic induction. These terms are representation of a surface area by a vector A, uniform magnetic field B, and magnetic flux phi B. The area of a plane surface is represented by a vector A drawn along the outward normal to the plane surface. In the case of a curved surface, the surface area is split into very small areas, and each is approximated to a planar area. In a uniform magnetic field B, the number of magnetic field lines cutting across an area placed perpendicular to the field lines is same for each unit area of the surface. If a plane of area A is placed in a uniform magnetic field B with its area vector A, making an angle theta with the magnetic field, then the magnetic flux phi B through the area can be written as phi B is equal to B dot A, which is equal to BA cos theta. Let this be equation 1. Magnetic flux phi B can be varied by changing any one or more of the terms B, A, and theta. The SI unit of magnetic flux is Weber or Tesla meter squared. Magnetic flux phi B is a scalar quantity. When the magnetic field has different magnitudes and directions at the various parts of a curved surface, the magnetic flux through the curved surface is computed by extending equation 1. Phi B is equal to B1 dot dA1 plus B2 dot dA2 plus and so on, which is equal to sigma all Bi dot dAi. Let this be equation 2. So far, we have recapitulated the terms used in electromagnetic induction. Let us now learn about Faraday's experiments where we use these terms. Faraday conducted 3 experiments, from which he concluded that an EMF is induced in a coil when the magnetic flux cutting across the coil changes with time. In the first experiment, Faraday observed that the relative motion between a magnet and a coil changes the magnetic flux across the coil. This change in magnetic flux with time induces an EMF in the coil. Similarly, in the second experiment, he observed that the relative motion between the two coils, one carrying a current, changes the magnetic flux across the coils. This change in the magnetic flux with time induces an EMF in the other coil. In his third experiment with 2 coils, he found that if the tap key is pressed, the current in coil 2 and the resulting magnetic field rises from 0 to maximum value in a short time. This results in a change in the magnetic flux with time across coil 1, inducing an EMF in it. If the key is kept pressed, there is a steady magnetic field across coil 1. Thereby, there is no EMF induced in it and the current drops to 0. When the tap key is released, the current in coil 2 decreases from a maximum value to 0 in a short time, resulting in the magnetic flux across coil 1 to drop suddenly, thereby inducing an EMF in it. From the observations of these 3 experiments, Faraday concluded that the time rate of change of magnetic flux through a closed coil induces an EMF through it, and stated the Faraday's law of electromagnetic induction. The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the coil. We can put this law in the form of a mathematical equation. E is equal to minus d phi b divided by dt. Let this be equation 3. In this equation, E is the induced EMF. The negative sign indicates the direction of EMF and hence the current in the closed loop. When n number of turns are closely wound to form the coil, the change of flux with time for each coil is the same, and we can write for the total induced EMF as E is equal to minus n into d phi b divided by dt. Let this be equation 4. In this equation, E is the total induced EMF. The negative sign indicates the direction of EMF and hence the current in the closed loop. Therefore, the total induced EMF can be increased by increasing the number of turns n of the coil.